Uh, hold on. What? Hi everyone. Good morning. It's April 15th, and this is our Calc 2 lecture. Yes. So today I wanted to talk about absolute convergence and conditional convergence, and perhaps get to a discussion of the ratio test, which for us will be a very important convergence test. And this will almost round out completely. I think we'll maybe have one more after this. Round out our suite of convergence tests. Okay? But before I do any of this new stuff, I do want to talk about the post-lecture slip that we did yesterday. So the slip from yesterday. So the 414 slip was to test the convergence of the following series. We had the sum from n equals 1 to infinity of the square root of n squared plus 3 over 2n plus 5 to the 6th power. And a lot of you submitted your slips correctly and all of that, but there were a lot of, very often, tiny little errors that I just want to point out. Now, this problem, as it happens, is very amenable to using either of the convergence tests that we talked about yesterday. So I think I'll do it both ways, okay? Yesterday we learned about the direct comparison test, and we also learned about the limit comparison test, and the pros and cons of using one or the other. I would say for a problem like this, my go-to, if I'm being honest, my go-to is always to use limit comparison test, because I know that limit comparison test is always going to be is always going to get me to arrive at the answer. It's more like things have to work out nicely in order for there to be a nice situation for direct comparison test to work out. And so to my mind, because of that, the direct comparison test is far inferior to the limit comparison test. But it just so happens that this series here is constructed in such a way that the direct comparison test works great. So let's see how that works. So DCT here stands for direct comparison test. And like I've been saying, it's important that when looking at a series, looking at the sequence of a series, it's important to make a determination as to whether or not that series there converges or diverges. So let's make a sort of a guess, or act on a hunch. Now, to me, the hunch, okay, the reason why I like LCT is because that hunch that you develop really comes from thinking about what the sequence of terms of an infinite series looks like when n is extremely large. We've sort of said this many a time, but when n is very, very large, because the thing under the square root here looks like a polynomial, the only thing that matters when n is large as far as polynomials are concerned are the highest order terms, right? The highest degree terms is what I mean when I say highest order. So in particular, this expression here, okay, the way I should think about it is that it looks like it's approximately equal to the square root of n squared over 2n to the 6th. In other words, this 3 here doesn't matter, and neither does this 5. Okay? When n is extremely large, both of the expressions n squared plus 3 and 2n plus 5, those expressions are well approximated by n squared and 2n respectively. Again, when n is large. Okay? Now, if I think about what this is here, I can expand out this expression, and what I get, let's see, 2n to the 6th, 2 to the 6th is 64, and the square root of 64 is 8. And so this denominator is 64n to the 6th power. The 6th binds to both the 2 and the 9, and the n. And then, so n squared over 64n to the 6th is 1 over 64 n to the 4th, and then the square root of that is 1 over 8n squared. Okay? So what I've done is I've approximated the sequence of terms when n is large by this expression, And this expression just purely algebraically is equal to 1 over 8n squared. Okay? Now, if the behavior of this thing looks a hell of a lot like 1 over 8n squared, that should lead me to believe that this series here is convergent. Why convergent? Well, because what I know is that if I take the sum from n equals 1 to infinity, not of this thing, not of what's inside the box, but it's what is inside the thought cloud here, 1 over 8n squared, then I know that that's going to be a convergent series. Why convergent? Again, because it's a constant multiple of a p series, where p is equal to 2. And since 2 is bigger than 1, I know that that p series converges. Okay? So, right. How can we use this insight? We believe this thing then is a convergent series. Okay? So if I want to use DCT to show... Oh, wait a minute here. If I want to use DCT to show this, then what I need to do is I need to find something which is, let's see, bigger than this. I need to find something bigger than this sequence, which when summed up will also be convergent, right? Okay, so let's see if we can do that. So first of all, I'm going to declare that this thing here, I'm going to call this a sub n. And what I seek in the direct comparison test is a b sub n, which is bigger than this, and which when summed up gives me a convergent series. So I'm going to work with this guy here. So the square root of n squared plus 3 over 2n plus 5 to the 6th. I'm going to work with this guy. And let's see here. So one way I can make something bigger, okay, one way that I can make something bigger, at least when n is big enough, I wonder what I should do here. Well, let's do it. I really dislike DCT here. Holy crow. I'm just realizing that it's not as nice as I thought it would be. Oh, okay. I've got an idea about how to go about this. Can we agree that if I replace this 3 here by 3n squared, that I get something bigger? Because n, remember, clicks through the positive integer starting at 1, right? So if I replace this 3 by 3n squared in the numerator, remember this 3 is in the numerator, then I get something bigger. So this is bigger than n squared plus 3n squared over, so there's one comment, right? The alligator would rather eat this guy. Now down here, if I want to make the entire fraction bigger, then one way I can do that is to make the denominator smaller. This is sometimes confusing, so make sure that you understand that. Smaller denominator means bigger fraction, right? So I'm going to make this denominator smaller, okay, by stripping away the both the plus 5, but also the multiplicative 2. I'm going to strip those things away, and so I get this. Can we all agree with that? Now this is equal to, there's no inequality here, this is equal to 4n squared divided by n to the 6th, which is also equal to 4 over n to the 4th, which is equal to 2 over n squared. Okay? So notice I have the inequality between the given series and this guy. This is going to play the role of my b sub n as far as the direct comparison test is concerned, and that is equal to 2 over n squared, right? So this is going to play the role of my b sub n as far as DCT is concerned. So let's just remind ourselves about what the direct comparison test says. This is the paper that I wrote up yesterday in the lecture. Here is the DCT. The situation is that if you have two sequences, a sub n and b sub n, which have this sort of inequality relationship, okay, then if the bigger brother converges, then so does the smaller, the little brother, yes? That was the conclusion. So what's playing the role of big brother here is 2n squared, and what's playing the role of little brother here is a sub n. Is that clear? So then we can conclude that since the sum of 2 over n squared converges. And why does it converge? Because it is a multiple of a p-series with p equal to 2, which is greater than 1, right? So since this thing converges, we conclude by dct the given series converges. Okay? So that's how you would kill this problem using DCT. At least that's the way I did. Okay? And you can see there was a little bit of thinking that I needed to do in order to get something which was bigger here at this step, which also had the property that the sum converged. Let's think about using LCT, though, in the service of this problem. Because this is, notice that the role that this thought bubble played, okay, the role that this thought bubble played in DCT was only to sort of develop this hunch that we had that this was a convergent series. Are you all with me there? Let's see. So as far as, we didn't actually use the specific detail of this 1 over 8n squared thing, which we estimated the sequence of terms to be equal to when n was very, very large. We didn't actually use that factoid. DCT doesn't really use all of that information fully. And that's, I think, a big reason why I personally strongly prefer the limit comparison test. It's because limit comparison test allows you to use fully the information contained inside of this thought bubble, which is, I think, a habit. This thought bubble is a habit that you should be that you should be adopting anyway, because it allows you to make hunches about convergence or divergence relatively quickly. So let's go ahead and see how the LCT fully uses this information. So what I'm going to do, again, this is going to be my a sub n for the purposes of LCT. Let's review real quick what LCT says. This is from yesterday. We talked about it. Here is the statement of LCT here. It says that if we have positive sequences, okay, then, and suppose that the limit as n goes to infinity of the quotient is equal to some number L, which is allowed to be 0, finite positive, or infinity. Then, depending on the nature of L, we can make one of 3 conclusions, and here they are. The most important one, for I would say, the most important one is this first one. If L is positive, then the sum of a sub n and the sum of b sub n converge or diverge together. The way that you'll choose b sub n with the goal of trying to get L to look like this finite positive quantity, the way that you'll choose b sub n is to think about what a sub n looks like when n is very, very large. That red thought bubble. You're going to do that red thought bubble, okay, as it pertains to your given sequence, and you're going to ask yourself, what does a sub n look like when n is very, very large? And you're going to use the resulting thing that your red thought bubble comes up with for your b sub n. So going back, here's my red thought bubble, and here's my b sub n then. So I'm going to let b sub n equal 1 over 8n squared. Okay? Then I'm going to look at the limit as n approaches infinity of a sub n over b sub n, but of course that's the limit as n approaches infinity of this complicated guy. Multiplied by the reciprocal of b sub n, right? Because I'm dividing by b sub n. That's the same as multiplying by the reciprocal of it. That's 8n squared over 1. Okay, now this is a moment where obviously you need some sharp algebra skills, and some of you really demonstrated some difficulty here. Here is how I believe you should proceed. there's a lot of ways to skin this particular cat, so don't sweat it if you didn't do it exactly the same way, but make sure that you're not making some very fundamental errors. For example, some people tried to convince me in their work that the square root of n squared plus 3 was equal to n plus the square root of 3, right? No, that's not right. That's completely wrong. That's completely wrong because the square roots do not play nicely with sums, right? There's no way of taking the square root of a sum of things and have that be anything really nice unless some grand coincidence should occur. In general, there is nothing that you can say about the square root of a sum. It's exactly the same situation as like a plus b squared. You know that that's not a squared plus b squared. You know a plus b cubed is not the same thing as a cubed plus b cubed. Okay, we need to get out of this way of thinking. Sums and powers don't play nicely with one another like that. Okay, the more technical way of saying it is that exponents do not distribute over sums. They do distribute over products though, right? That's one thing that's nice about exponents, but they don't distribute over sums. Okay, so in particular, even though I see square root of n squared plus 3 up in the numerator here, I can't do anything with that, so I just leave it alone. Now listen to me. I will say this because I don't want to deceive you. If you did write the square root of n squared plus 3 as n plus the square root of 3, I made a comment about that in the email, if I caught it. I made a comment about it because I don't want you to labor under the delusion that that is the truth, okay? Because those two things are not equal. However, I will say that for the purposes of taking a limit as n goes to infinity, it's actually fine. And the reason that it's fine is because when thinking about n going to infinity, oh, and I messed up here. When thinking about n going to infinity, the 3 doesn't matter, right? When n goes to infinity. So of course, the limit as n goes to infinity of square root of n squared plus 3 is the same, or is equal to n plus the square root of 3. And not only that, but it's the same asymptotically. That is to say, those two quantities are equal enough when n is very, very large that they are equal on the nose in some sense when n goes to infinity. But these are all complicated considerations that I don't think that you're taking fully into account when you write square root of n squared plus 3 is equal to n plus the square root of 3. I just don't think that you're thinking that, okay? So that's why I corrected you, even though in some sense you're right. You're not wrong. Anyway, let's keep going in the problem. Then we have n squared, 8n squared over 1. Notice that I took the square root of 2n plus 5. That's the same thing as raising to the 1/2 power, which is the same thing as multiplying 6 by 1/2 to get 3, this new exponent. Okay? All right, so now what do? So what a lot of people elected to do was to expand out this 2n plus 5 cubed. And sure, you can do that, but I would suggest going a different way. I would suggest that factoring out an n squared from what's underneath this square root is a sweet move, but also factoring out a 2n from what's inside this cube is also a sweet move. So let's see that. So I'm going to rewrite the square root up there in the numerator as n squared times 1 plus 3 over n squared. Yes? And then I'm going to have this 8n squared up there as well. And then downstairs, I'm going to factor out a 2n. I'm taking a long time on this. I'm nearly 20 minutes in. I was hoping this would only take 10 minutes. Big fucking joke, right? Okay, so now I can pull out this n squared. Now if I pull out the n squared from underneath the square root, when it comes outside the square root, it becomes the absolute value of n. But n here is running to infinity, so that's just the same thing as n. So this is n times the square root of 1 plus 3 over n squared. And this 8n squared, I can multiply it by this n to get 8n cubed. Okay? And then downstairs, I know, like I said, exponents distribute over multiplication. And so this denominator is equal to 2n cubed, which by the way is 8n cubed, times 1 plus 5 over 2n, this whole thing cubed. Now note that as n goes to infinity, these things that look like constants over things involving n that go to infinity die, right? They go to 0. Similarly, well, not similarly, but also note that those terms there cancel. This cancellation really is the whole thing that we're aiming for, and it's the reason why this b sub n is so kick-ass, right? Because it causes this these things to cancel, and what we are left with is 1. And this 1 confirms for us that the red thought bubble that we had really was legit, really was the truth. That when n is extremely large, this and that are basically equal to one another. There's no difference. And you can see that because the limit of the quotient is equal to 1, thus suggesting that when n is around infinity, that is to say when n is super large, a sub n and b sub n are basically equal. That's the only way the quotient could be equal to 1 in the limit. Okay? Hopefully that makes sense. Okay, so what is the conclusion? We're not done. This is not what we box. We draw a conclusion from this. The conclusion is that by LCT, the given series and the sum from n equals 1 to infinity of 1 over 8n squared converge or diverge together. That's not the conclusion of the problem either, because we need to make then a determination as to whether this guy here converges or diverges. What do you think? Well, I hope that it's almost involuntarily the case for you, that it arises in your mind that this thing here converges. The latter you should know is a word that means the second, when you, I don't know, do you know English? The latter series converges as it is a multiple of a p series with p equal to 2, which is greater than 1, thus guaranteeing convergence. Right? You need to have that p series result in there in order and be able to use that at any moment. Okay? Therefore, the series converges. Okay? All right. So that's the what? Oh yeah, that was the slip from yesterday. A very extended discussion. I think it's worthwhile. Okay, because you know this type of problem is sort of, I hope, will be bread and butter for you as far as infinite series and such are concerned. I'm used to in-person things, and at this point I would ask, are there any questions about anything? And if you do have any questions, please just pop them in the chat. I've got the chat open there and I'm sort of keeping an eye on it. Okay. Then let's talk about this notion that I mentioned, absolute convergence / conditional convergence. Okay, so definition. An infinite series, I'll just say a series, sum of a sub n, is said to be absolutely convergent. So this is a new adjectival phrase that we are going to apply to series. A series is absolutely convergent if if the sum of the absolute value of a sub n is convergent. Okay, that's what absolute convergent means. How about conditionally convergent? A series is conditionally convergent. if two things. It is convergent and the sum of the absolute value of a sub n, this guy here, is divergent. So these are the two new definitions that I would like you to absorb. So if you think about these two definitions. So think about these two definitions and then think about the following claim that I'm about to make. The claim that I want to make is that these two notions, conditionally convergent, absolutely convergent and conditionally convergent, cleave the space of convergent series into two parts. We now have the world of absolutely convergent series and conditionally convergent series. That's my claim. That these are now sort of two states within the broader territory or country of convergent sequences. And that there is no space left over in particular. This is the picture that I want you to have in your mind. But do these two definitions really sort of, do they really suggest that to you? Or is there a piece here that's sort of missing, maybe, that logically maybe would suggest to you, or maybe would suggest to you that the claim that these two categories of, that these two concepts don't actually take the set of all convergent series and sort of give a dividing line between them with nothing left over, nothing left out. That, what am I, sorry, maybe I'm being too abstract about this. All I'm trying to say is that every convergent series is either absolutely convergent or conditionally convergent. That's my claim. Okay? Now, in reading these two definitions, is it really clear that that's the case? So the first one says merely that you have a series which is absolutely convergent if this guy here is convergent. The second statement here is saying that it's convergent if not only the given series is convergent, but that this thing is divergent. So doesn't it kind of make sense that it cleaves the thing into two pieces? Although the sort of logical possibility, I think, that maybe is left out, the logical possibility that's left out is, what if you have a divergent series which is absolutely convergent? Is that possible? Can you have a divergent series which is absolutely convergent? That is to say, can you borrow series from the country over here of the divergent series? Can you borrow some things over there and throw them into the absolutely convergent pile? The answer is no. And there's something called the absolute convergence test, which delivers the death blow to that idea. And we'll abbreviate this ACT. Okay? And here is what it says. It says that if a series is absolutely convergent, then it is convergent. See, that's not, this fact is not included in this statement of absolute convergence, right? It is not, strictly speaking, a requirement of an absolutely convergent series that it converge. Okay. I think that's what this is called. Yeah, that's what this is called. Okay. Yeah. Sorry. I'm all over the place today. My brain is. So this is a very important fact. Now, what I want to say is that the question that I want to ask now is whether or not the converse of this statement is true. That is to say, if you have a convergent series, is it necessarily absolutely convergent? And I think that given that I've defined this notion of conditional convergence, it should be obvious to you, just based on the structure of this lecture, or that the fact that I've written down a notion called conditional convergence, it should be obvious to you that the converse of this must be BS, right? The converse of this must be a big old steaming pile of butternut squash, right? Can't be true. And the reason, it's because I wrote down this thing, conditional convergence, which describes a situation for a series which is a direct contradiction to the converse of this statement. Directly serves as a counterexample. It could be that this is a completely vacuous notion, however. By that I mean, like, I've defined the notion, I've told you what the conditions are, but maybe there are no actual examples out there of series which satisfy this definition of conditional convergence. That's not the case, as we will see, but maybe at this stage in your life, maybe I'm lying to you, and who knows? Why should you believe a single thing I have to say about anything? I don't know. I'm not lying to you, but it's good to be skeptical about these things because, God, what is my incentive to tell the truth? It'd be so much easier. My life would be so much easier if I could just lie to you all the time. I think about this a lot. I don't know if you're aware of this. But somehow I feel like whatever. Let's not get into that. Okay. I want to also introduce today alternating series. Maybe I'll do that over here on this side, okay? So alternating series are a series of the following form. Definition. A series is alternating. And I'm going to give you a formal definition because I love you, but the basic idea is that it just flip-flops in sign from term to term. The sequence of terms goes from negative to positive to negative to positive. And that's what an alternating series is. A series is alternating if it can be expressed as either the sum from n equals, I'll just write it like this, the sum of negative 1 to the n times a sub n, and to make clear that this a sub n here is always going to be positive, I'm going to write it as the absolute value of a sub n. Okay? Or the sum from n equals 1 to infinity of negative 1 to the n plus 1. All this of the absolute value of a sub n. All this does is, instead of starting maybe at negative 1, starting with a negative term, it starts at a positive term, right? So let me very quickly give you examples. But before I do that, let me just give you the intuition. All this means is that the sequence of terms it's really hard to do this lecture thing online, because like usually at this stage I would look out into the crowd and I would into the audience, and I would see how many of you have this very characteristic eyes glazed over gaze staring off into space. And by that, I can sort of measure how confusing I'm being, if I'm making any sense at all. But right now, all I see is a piece of paper in front of me, projected onto my computer monitor, and holy shit, it makes perfect sense to me, right? So I have like no idea where you're at, like none. I have zero idea where you are at right now. So I'm really hoping that you will be super forthcoming with any confusions that you might have in the post-lecture slip, because that's the only way that I can know whether you're getting this or not, like in a non-high stakes setting. So if I am being confusing, and I have a feeling I might be being very confusing right now, please let me know. All this means is that a sequence of terms flip-flops between positive and negative. I swear I'm going to give you an example right now. The examples are easy to write, okay? Because, for example, here's probably the most famous alternating series. It's called the alternating harmonic series. Here it is. It's the sum from n equals 1 to infinity of, let's see, I want to get the sign right. It's negative 1, I believe, to the n plus 1 power over n. So what is this series here? Let's just write out the first few terms. So when n is equal to 1, what do we have? We have, this is 2 up here, and that's 1. Negative 1 squared is 1, so the first term is 1. When n is 2, this becomes 3. Negative 1 to an odd power is always negative 1. Then we have a 2 downstairs, so we get minus 1/2. The next term will be plus 1/3, minus 1/4, etc. You see the pattern, right? This is called the alternating harmonic series because it looks like the harmonic series, except that it's alternating. Why is it alternating? Because you can see the sequence of terms flip-flopping between positive, negative, positive, negative. The tip-off that you're looking at in alternating series is this negative 1 to the blah gadget that we see here. That's usually an indication that your series is alternating. Usually. You just want to be careful about that, because what if I put some goofy power on the negative 1? Yeah? Okay. Hopefully that's clear. And so when given an alternating series, it's important to know whether or not this alternating series converges or not. And we have a great result in that regard, which we are going to call the alternating series test, which we will abbreviate AST as usual, initialize it. And what does this result say? It says that an alternating series which is either, remember, negative 1 to the n times the absolute value of a sub n, or the absolute value of negative 1, sorry, the sum of gonna not talk. So an alternating series is either of that form or of that form, is convergent if and only if the absolute value of the limit as n approaches infinity of the absolute value of a sub n is equal to 0. So you should be having memories of the divergence test. Remember what the divergence test says. The divergence test said that the only way that you could possibly have a convergent series is if the limit as n approaches infinity of the sequence of terms is 0. That's what the divergence test says. But now look at this statement. This statement says that not only must you have, I mean, obviously this condition here, that the limit as n approaches infinity of the absolute value a sub n, means that the sequence of terms of either of these alternating series representations, either of them, obviously this condition means that the sequence of terms goes to 0. But it's stronger than that, because whereas the divergence test says that it is necessary for the sequence of terms to go to 0, that is to say, it is necessary that for a convergent series, the sequence of terms goes to 0. It is necessarily the case that the limit of the sequence of terms goes to 0. For an alternating series, not only is it necessary, but it's also sufficient. That is to say, as long as you can see that the sequence of terms goes to 0, and in particular, as long as you can see that the limit as n approaches infinity of this sort of non-negative part, the non-alternating part of this infinite series here is going to 0, that is sufficient to guarantee that the series is convergent. You hear these phrases, necessary and sufficient, a lot when you get into sort of the deep depths of sophisticated thinking around mathematics. Okay? And you all, as engineers, are not immune from that. So I hope you don't believe that. But it's worthwhile to think about what those words necessary and sufficient mean, particularly in this context. Okay, so now let's think about what the alternating harmonic series looks like. What is playing the role of this sort of absolute value of a sub n thing? Well, what's playing the role of that is the 1 over n, right? The alternating gadget is the negative 1 to the n plus 1. So, example. Let's go back to our alternating series test. Oh, sorry, our alternating harmonic series. This guy. And we can determine that this is convergent because the part of this thing, which is sort of the non-alternating part of it, the positive part of this guy, is 1 over n, right? The alternating gadget is the negative 1 to the n plus 1. This is convergent because the limit as n approaches infinity of 1 over n is equal to 0. That fact, and maybe I'll say it like this: this is convergent by virtue of the AST. Is convergent because the limit as n approaches infinity of 1 over n is equal to 0. That is enough to guarantee that this is a convergent series. Okay? Cool. So, then, we learn the following fact. So, therefore, we have the following situation. Alternating harmonic series. First of all, it converges. Why? We just showed it. We just showed that it converges. On the other hand, it is not absolutely divergent. What? Fuck me. Holy shit. What the hell did I just say? It is not absolutely convergent. I know these are new words, so let's go back and remind ourselves what these words mean. Absolutely convergent means that the sum of the absolute value of the sequence of terms is convergent. I don't know why I wrote these points over here. There, I covered up my mistakes here. It's convergent, but it is not absolutely convergent. Why is it not absolutely convergent? Because if we look at the alternating harmonic series and we take the absolute value of it, okay? Well, this is equal to the sum of 1 over n. Does that look famous? That is the harmonic series. Okie doke? That's the harmonic series, people. And so it is famously divergent. So we have a series which is convergent, but it is not absolutely convergent. And so look at the definition of conditional convergence. It is conditionally convergent. This implies that the alternating harmonic series is conditionally convergent. Okay. And in fact, the alternating harmonic series is probably the most famous example of an of a conditionally convergent series. Okay. Conditionally convergent series are very strange. They're very, very strange beasts. For example, Riemann proved that when you have a conditionally convergent series, it turns out that, don't think about this too hard, it's not going to be terribly relevant or important for our class, but it's a fact that when you have a conditionally convergent series, you can rearrange the order of the terms of a conditionally convergent series. So remember, this is the harmonic series. It's a alternating harmonic series, rather. Its terms look like this. You can rearrange the terms of this conditionally convergent series. Remember, this is convergent. You can rearrange the terms of this conditionally convergent series and obtain any number that you want. Literally any number that you want. Pick a real number, any real number. You can rearrange the terms of this infinite series here in such a way that if you think about the limit of the sequence of partial sums of that reordering of the alternating harmonic series, you can make that limit equal literally any number that you want. Is that not bananas? That was something that Riemann proved. Riemann is one of the goats as far as math is concerned. You can make it converge to literally any number that you want, and that's fascinating. What about this ordering? Maybe you can ask the question, what about this ordering? What does 1 minus 1/2 plus 1/3 minus 1/4, what does that converge to? That's a good question. I believe that it converges to natural log of 2, which is really weird, right? Why does this thing here converge to natural log of 2? Well, actually, I think we'll be able to figure that out when we learn about Taylor series. You know, maybe it'd be cool if I did a Python script. I'm a little scared to do it, but if I did a Python script which could approximate this thing. I'm a little scared to do that. Oh, maybe I'm not scared. Maybe it's okay. Oh, I don't know. I'm a little scared. Anyway, yeah, I should give you a post-lecture slip and not waste your time. So let's do that. Well, what should we do today? I'm going to make it what I think of as being a very simple question. I just want you to sort of unwind some definitions. 1. Here's the, so 1, what are you confused about? That's what I'm actually most interested in. Okay, and 2, so this is for what day? 4/15. Do I have to pay taxes today? It is tax day, 4/15. I know that there was some announcement that maybe the tax deadline would be extended to June. But I don't want to mess around if I'm supposed to, you know, like messing around with taxes is a bad move. And 2, I'm sorry, I'm totally wasting your time. And I'm getting paid for it. What are you confused about? And true or false? This series is conditionally convergent. true or false? This series is conditionally convergent. What series? This series. The sum from 1, n equals 1 to infinity, of negative 1 to the n, plus 1, let's say, over n squared. Let's just keep it real simple. So I believe that this is, the terms of the sequence, I think, are 1 minus 1/4 plus 1/9 minus 1/16 plus 1/25, etc. Okay? And my question to you is this thing conditionally convergent? And I want you to justify it. Oh, maybe I'll make that question 1. Question 2, true or false? This series is, that series is absolutely convergent. Wait, this is so stupid. Really, I'm just asking you, well, I guess it could be divergent, and then it's neither. Is it one of these two? Is it neither? I guess this is a good question. Okay, so I want you to, for part number 2, I want you to determine for me whether this is conditionally convergent, absolutely convergent, maybe it's neither, maybe it's both. Okay, I want you to tell me what you believe. And I want you to justify this as well. Okay? Alrighty, I love you very much. For those of you that are, maybe for those of you that are interested in simple programming stuff, maybe what I'll do right now, I'm going to end the lecture right now, but maybe what I'll do is do a little Python script, because I'm curious if I'm right about the alternating harmonic series, to see whether or not it converges to log of 2. So let's see here. How can I do this? I can add a window capture. So, please, if you don't want to see programming, just leave. Okay? I love you. But if you do want to see this, then just take a look. Because I'm curious, and I might as well do this on stream, right? I've got some time. Let's see. Let's not show my whole desktop. Terminal. Where's my terminal? There it is. Okay. Okay, so wait, there's my terminal. Wait, actually, I should open a new terminal because I'm running OBS out of this terminal. Huh? Okay, so instead of that one, let's make it be the other. What is going on? Wait a minute. Oh, wait, that worked somehow. Okay, can you see my terminal there? Okay, so let's see, Python. So what I want to code in there is an approximation to the value of the alternating series test, which I've got here. So I'm going to start by declaring a variable which is equal to sum. I'm going to start it out to be 0, and my plan is to add to this variable sum the terms of this sequence. That's my plan. So let's say for I in range, I don't know, 100, because why not? I'm going to take sum and I'm going to add to it. So what this means, so the equal sign, one equal sign in Python is an assignment operator. It is not a test as to whether or not two quantities are equal. So what this is going to say is that I'm going to store in the variable sum the previous variable, the previous value contained in sum, plus the next term in the alternating harmonic series. Okay, I don't know if that makes sense to you. Now, if I have I in the range 100, range 100, what it is in Python is a list of numbers. the list starts at 0. This is sometimes confusing. It starts at 0, but very common in computer programming. It starts at 0, and it clicks through the positive integers until it hits, actually, I think in previous videos I might have said that it hits this last value of 100, but in fact it doesn't. It stops at 99. It gets to 99, and then it doesn't get to 100. So that there are in total 100 terms. If you include 0, there are 100 terms in this list. It goes from 0 to 99. So sum is equal to sum plus, and now what I'm going to add is 1.0 divided by, and actually I need to do the alternating thing. So I hope that this will work. 1.0 divided by I. Now, because I starts at 0, I need to do I plus 1 as my denominator. So that's the non-alternating part of the alternating series. And what I'm going to do is multiply this by I to the nth power. No, negative 1 to the i's power. My bad. Negative 1 to the i's power. And the stupid way that you do powers in Python is like this. Now let me just think through. So when I is 0, when I is even, this pow of 1, this term right here, pow of negative 1 to the i's power, this guy here is going to be positive 1. And when I is odd, this will be negative 1. So I think this should work out. And then what we'll do is we will print at every step through this for loop here, we'll print the value of sum to see if it's doing the right thing. Gosh, I hope so. I don't know. I'm a little nervous. Okay, cool. So here we got our list of numbers. We can see it starts at 1. That's because the first partial sum is just 1. The second partial sum is 1/2 because the second partial sum is 1 minus 1/2 in the alternating series. Then we add 1/3 to 0.5. And indeed, we should get 0.8333333, etc. Then I guess we subtract a quarter, then we add a fifth, and you can see this list of numbers. And what we see as we move down this list of numbers, as we get deeper and deeper into the sequence of partial sums, we see these numbers getting closer and closer to some value, which looks like 0.688. Now what's interesting about this is that we're still just in terms of precision, it looks like we're still just in the hundredths place of the decimal, right? Like look at this number here. This is the 100th term. This is the 99th term, right? And we're still in the 100th place of the decimal. So in other words, this thing is not converging very quickly to whatever it's converging to, and it does feel like it's getting closer and closer to something. It's not converging very quickly. But of course, one of the awesome things about computers is that you can make it do much more precise things. So if we reset sum to 0, and then instead of having I go from 0 to 99, let's have it go from 0 to 9,999. Okay, so instead of computing the 100th partial sum, let's compute the 10,000th partial sum, or the 9,999th partial sum, because I suspect that we'll get a lot more accuracy that way. So we're going to want to do the same play, and we are going to want to print sum, and I believe this will give us a whole lot of numbers. Okay. So now look at the how close these numbers are together, right? 0.693, 0.693. It's still off in the 10,000th place. I mean, all of this kind of makes sense. Point is that, if you want 3 decimal places of precision, you're going to probably need at least maybe 1,000 or 10,000 terms, something like that. I think 1,000 would probably do. Okay, well, anyway, what is the natural log of 2? So I don't even know if Python has how does import I do this? Import math. How about that? Math.log. Math.log of 10. What does this do? Okay, so this looks like the this looks to me like the that log math.log is a function from a library which is the natural log. That's very common in math and physics. Log is just a synonym for the natural log. I know that for a lot of other fields, log is a synonym for log base 10, but that's not the case in math. And if we look at math.log of 2, you can see that it's very, very close to the value of this 9,999th partial sum. Or the 10,000, I think it's the 10,000th partial sum. I'm not sure why I'm saying that. The 10,000th partial sum here, which is 0.693. And down here we have 0.693147. And so if we were to run that script, computing 100,000 terms, we would suspect that we get it closer to this. And if we run it with 1,000,000 terms, we get closer and closer to this. Okay? Cool. By the way, also, here's another crazy fact. Another crazy fact. Oh, maybe I won't give this away. Never mind. Oh, whatever. If you made it this far, then you'll probably get this question anyway. But this is, in fact, a convergent series. You see the one I'm pointing at? That's convergent. And I think that it converges to pi squared over 12. I'm not totally sure if that's true or not, but I think it might. So you might be interested in trying to test that numerically for yourself by mimicking the Python program that I've done here. Yeah? And you can very easily do that. Please understand that this computation, though, is not an exact calculation. Rather, what it is an approximation. But a lot of times, approximations are just fine for developing insights, or even for building skyscrapers and such. Okay, that really does end it. I just wanted to do that because I wanted to do that for my own edification, and I think that, can I be real with you? I think that learning a computer programming language is basically the most important thing that you can do while you're a university student. I mean, math is very important, reading is very important, but I think that computer program is very quickly becoming maybe third place and maybe second place. I don't know. It's super important. Put it this way. I've got 2 kids right now, okay? 2 kids. And the most important thing that they can learn, aside maybe from their reading and arithmetic, is computer programming. So I highly encourage you to, if you have spare time this summer, because maybe cruise is canceled, or if, I don't know what, your internship is canceled because of coronavirus, try learning Python. Try it. You'll be so much stronger at the other end. Really. Love you all. Talk to you soon. I'm going to open up Zoom office hours. Okay.